Okay. I'm going to talk about semi-continuity theorem. The main point is from several complex variables, but this thing has a deep root actually, and so the title is a little bit too big. As I was reading from a chair, it's a little bit big, but anyhow, let me give a try. I'm talking about the paper, still in progress, but it's almost finished, but still in progress in the sense that if you want a preprint of it, you'll have to wait a couple of months at least. So these are the authors, and the fourth person is most interesting and important. She's over there. She's my student. The colorful shirts. Okay, so I'm going to talk about general principle. Sorry about dumb looking, what's going on here? Yes, general principle. General principle which existed for a long time in geometry, even in Euclidean geometry, is that if you have a very symmetric figure, say a line, for instance, in order to ruin the symmetry, you can ruin it by an arbitrarily small effort. On the other hand, if you want to create the symmetry, then you need a definite action. I mean, this is the usual term. I don't use this kind of term, but Robert Greene, my teacher, likes to use this type of term. So I respect him. So I put that term over here. So that's when I mentioned Robert Greene's term, I would say that this is a principle of life, he says. That's a little bit too big. Anyhow, what I'm saying is that if you have a non-symmetric figure, in terms of Hausdorff distance, comparing two sets, for instance, in a very small neighborhood, let's say a very small epsilon and take a small epsilon neighborhood in terms of Hausdorff distance, then in the neighborhood there are only non-symmetric figures. There aren't any symmetric figures nearby a crooked line, for instance. If you have a very small epsilon neighborhood, then everything in there are crooked lines. It cannot be straight line. But in an arbitrarily small neighborhood of a straight line, there can be many irregular figures actually. In terms of convergence, here's another illustration with a compact figure, for instance. If you think about the sequence of ellipses, so this time I'm going to use sequences. So as if it might look as if I'm saying a contradiction all by myself, but I'm changing the viewpoint. I'm talking in terms of convergence. You can create a sequence of ellipses that converges to a sphere. That's possible because you change ellipses gradually, and then it can converge to a sphere. It can converge to another ellipse too, but it can't converge to a sphere. But if you take the sequence of spheres, that can never converge to an ellipse. It only converges to a sphere if it converges at all, right? So that's the semi-continuity idea that from here to there, as figures converge, symmetry increases in the limit. Does not increase continually, but not continuously, but it increases at the limit suddenly. And the very symmetric things can converge only to symmetric things, and the other way is not possible. So from here to there, that's not possible. Obviously, this thing has more symmetry than this one. So that's the principle. It's fairly shocking at first sight, but if you think about it, it's the general principle, really. As Robert Greene likes to put it, this is a general principle of life. If you want to ruin the harmony, you can use arbitrarily small effort, but if you want to create harmony, that requires definite action, he says. Okay. All right. The differential geometry, Riemannian geometry, theorem formalizing this thing. Actually, there is one more prehistory, but I'm not giving a history lecture, so I'm going to directly dig into Riemannian geometry theorem. This was by David Eben. I'm not sure I'm pronouncing his name correctly. Close enough, I guess. Eben. And the paper came out in 1968 in the Bulletin of the American Mathematical Society. Quite a historic theorem. And the way he organizes the theorem is in this way. Let's look at a compact Riemannian manifold. So compact smooth manifold. This time we are not going to discuss, we can discuss, but it's the same. Instead of discussing the convergence of Riemannian manifolds, we can do that in some smooth sense. Let us discuss in this way. Let's fix the underlying smooth manifold, compact smooth manifold. And then we think about the sequence of, what's going on here? Sequence of Riemannian metrics. Because when Riemannian manifolds converge in a very strong sense, such as in C-infinity sense, for instance, then the tail part of sequence, all manifolds are diffeomorphic. So let's say underlying manifold is just fixed. And then let's think about the metric converging, okay? And for each metric, let's think about G0, which is the group of isometries of this Riemannian manifold. Okay. And then the theorem of Eben says that for G0, there exists some neighborhood. Now we are talking about metric tensors. So in some sense, they are functions. They are functions. And so we can talk about C-infinity neighborhood in terms of comparing the function, derivative, second derivative, etc., everything all together, right? Okay, so let's think about some neighborhood of this Riemannian metric. Then the claim is that there exists a small neighborhood such that for any metric nearby, G0, the isometric group is a subgroup of G0, isometric group of HG, right? So this is the isometric group of this metric nearby G0. This is the isometric group of the limit metric. And the limit metric has larger isometry group. In the sense that he says a little bit more than what I said, is that for any G, the metric G, the isometric group can be conjugated by a diffeomorphism from M to M in this way, so that the conjugation is actual subgroup of G0. It's contained in.
Do you know, can you take phi equals the identity here?
No. No, not really.
It doesn't apply, I'm just like, can you?
Excuse me?
It's not known. I'm just wondering, can you, is this still true with phis?
I guess not. But I cannot give you a very accurate answer, sorry. Can phi be the identity? Actually, can it go in? I guess not.
Usually, often, almost always, wouldn't phi G, phi inverse just be the identity?
Not necessarily.
Most Romanian metrics don't have assignments, right?
Oh, in that sense, yes. Because it's a trivial group. In that case, yes. The most, yeah, I missed the most. Yes. Okay. All right, so this is a Riemannian geometry theorem. I'm going to discuss a proof. I say a proof because this is different from original Eben's proof. But I'm going to discuss the proof briefly throughout the lecture. Okay. And that's a Riemannian geometry thing. And what Eben's theorem says, sorry about repetition, is that if the Riemannian metric converges in C infinity sense, then isometry groups increase at the end, at the limit. So that's what I call semi-continuity. As you take the limit, the isometry group suddenly increases at the limiting point. So that's what I say. That's what the semi-continuity terminology means. In case when K is pretty big, then tail part, the isometry groups can be conjugated so that they can be realized as an actual subgroup of the target group. That's what the Evans theorem says. Okay. Now I'm going to discuss how to prove this thing. All right. So here's the proof which is known. Actually, it's not something we discovered newly. It's known. Now that we are counting the derivatives in the several complex variables version later, I'm going to discuss this thing. Let's just go on, and you'll see it eventually. So this triangle is Laplacian, Laplace operator. So on a compact Riemannian manifold, let's think about the Laplacian. And then we take eigenvalues and eigenfunctions of this Laplace operator for this Riemannian manifold. Spectrum is discrete, right? And we have eigenfunctions. And then if you take enough number of eigenfunctions, then you can use those eigenfunctions to embed manifold into a Euclidean space. Howard wrote Rn. This is En, same thing. The Euclidean space, n-dimensional Euclidean space. This number is pretty big, but still we have an embedding. And this embedding is interesting in the sense that the isometries of M preserve eigenfunctions of Laplacian. And so isometries can be realized as an orthogonal subgroup of an orthogonal group of En, because each basis is in terms of isometry, they change, but they are preserved in that sense, right? And so suddenly we started with Riemannian manifold, but through this embedding, what is called equivariant embedding, through this embedding, you have this isometry group realized as a subgroup of an orthogonal group. No, not really. No. No, isometry group is much smaller, actually. So, yeah, each isometry is an orthogonal matrix. Yeah. So, okay. So subgroup of isometry group is realized as subgroup of orthogonal group. Okay. Once you do that, and then you think about the convergence of Lie subgroups. So you do this procedure for each GK converging to G0, for instance, right? So if you do that, then you have a convergence of pretty weak sense, but the convergence of subgroups. In a huge orthogonal group, you have groups converging to the target group. Once you do this, this is even older theorem than Evans theorem, Bochner-Montgomery, I suppose. 1958, as I checked. It turns out that when groups converge, these are compact groups, it's very funny that if you take the limit of the group, and then you take the target group, you take epsilon neighborhood in pretty weak sense. But if you take the neighborhood of the group, of course, epsilon delta argument says that your group GK should be inside that neighborhood, right? It could be outside the target group. But the fact of Lie group says that if that happens, all these compact groups are actually subgroups. Yeah? And so not to answer to your question, but the method we are using cannot avoid conjugation, because the thing is conjugated by this realization over here. Yeah. Okay. Then you have this subgroup situation over here, and then you unconjugate. Then you have semi-continuity theorem, as I explained. So sometimes people are not happy when they don't see the formula. So I'm going to tell you this. This is analyst Laplacian. So I write this way. Eigenvalue is lambda. These are positive numbers. And so we think about the eigenfunctions. And continuity of spectrum and eigenfunctions. This thing shows that if we change G slightly, still this thing is an embedding. So we have lots of embedding. And then this number, you might think this is suspicious, but the spectrum is discrete. So you have enough gap to move over there under perturbation. So you have a realization. I mean, here's an isometry. And here's the embedding using the eigenfunctions. And so you have this realization over here, which is a conjugation by this map F. Here's the isometry. And then you realize this thing as a subgroup of an orthogonal group. So as I said, the convergence of compact subgroups, and the orthogonal group itself is compact. And so convergence of subgroups with Bochner-Montgomery theorem gives Evans theorem. This is known, by the way. It's not our new invention or anything. This is known, and this is probably the nicest, as far as I know, nicest proof of Evans theorem. Original Evans theorem was so complicated. It used complicated discussion about Sobolev spaces, so it required C infinity everywhere. But now we can do it with C2, just enough to use Riemannian geometry, very low level. And the interesting thing about Laplacian with the great regularity thing just allows us to carry out all this argument, elliptic regularity. So there's no high differentiability required in this part. Is this okay? All right, so let me continue. So, right, I already explained this. And then I'm going to go into a very classical several complex variables now, where I live in. I used to joke with Professor Chung Kyo-han that he's old-fashioned, but I'm actually living in a very old several complex variables here. Okay, so let me explain what Green-Kranz theorem is. This is 1982. This paper, actually, this theorem appeared in Mathematischen Annalen, but this was based upon their very thick paper in Advances in Mathematics a year before. Anyhow, let me explain this. So here's one target domain, a bounded, strongly pseudo-convex domain in Cn. I'm not going to explain what that is. One thing I'd like to say is that up to biolomorphic equivalence, strong pseudo-convexity is just strong convexity, actually. So you need two derivatives to define this boundary, this type of boundary. But here requires C infinity smooth boundary. I'll tell you why, but this was the theorem in 1982, quite some time ago. Okay, it says not biolomorphic to ball because the ball, which is obvious prototype of strongly pseudo-convex domains, has a non-compact automorphism group, and that's way too big to handle here. We are talking about only compact groups. Yeah. Okay, so not biolomorphic to ball. Then there's famous theorem by Wang, Bon Wang, that this domain has compact automorphism group. Okay. If you do that, then we say, again, we are in sort of Hausdorff type distance. So in an open neighborhood of omega, so omega should be understood as an element. But then you can compare two elements by comparing defining functions, for instance, or using diffeomorphisms, which are very close to identity, etc. anyhow, you can define C-infinity topology, which is well known, so I'm not going to discuss this. There exists a neighborhood so that any element in the neighborhood, that's another bounded strongly pseudo-convex domain. Now let me separate the theorem into two pieces, but they stated in this way. Say automorphism group of a nearby domain has to be smaller, in my sense, than the automorphism group of the target domain. These are compact groups. And that the smallness can be realized by diffeomorphism. This F and this F, their fonts are different, but they are the same F. So this CL means closure. I used to use bar for the closure, but some people are angry in complex analysis if I use bar for closure. So this is closure. So from closure to closure, there's a diffeomorphism so that you can conjugate this group so that each element, even though it is conjugated by just diffeomorphism, it's a holomorphic map, and that's part of automorphisms of the target domain, the limit domain. So that's Green-Krantz. But why do you need C-infinity? Because if you look at just the statement, you don't seem to need that many derivatives, because strong pseudo-convexity requires only two derivatives, etc., etc. So, Well, before I go, I guess Howard stole my show. But even in complex analysis also, if you think about the domains that are very close to the ball, approximation of ball, that's strongly pseudo-convex, as Howard said in the previous lecture. Strongly pseudo-convex domain. And this famous paper says many things. One thing is that for those domains in dimension 2 or higher, in dimension 1, Riemann mapping theorem says that those are all simply connected bounded. Therefore, those are all disks. And so just a disk up to biolomorphism, so we are not gaining anything. But in dimension 2 or up, most such domains have just one element in the automorphism group, which is the identity map. So there's nothing to prove in most cases. But still, there are many, nowhere dense, but still many domains in terms of numbers, more than my fingers can count, actually. Domains that have large automorphism groups, still compact. There are many. And then if you think about how many, then here's another theorem. I wrote two papers. Any compact Lie group is realized, meaning that Lie group isomorphism, to the automorphism group of a bounded strongly pseudo-convex domain. So if you think about it, there are many groups appearing, all compact subgroups, compact Lie groups appear as automorphism groups. Okay. Now I'm going to explain how this theorem goes. Right. I don't have to hurry, right? Okay. One's theorem says that if bounded strongly pseudo-convex domain has non-compact automorphism group, and then the domain is biholomorphic to the ball. This mighty theorem explains why I needed that. The Green-Krantz theorem needed that statement, that assumption that the target domain has to be non-biholomorphic to the ball, okay, because we are dealing with only compact groups. Okay. And then before I go to the next box, let's think about how to prove it without knowing anything. So we have the domains converging to the target domain. Let's forget about all this complicated, fine definition of C-infinity convergence. Let's just think about the domain just perturbing and converging to the limit domain. We have automorphisms going from, say, omega j to omega j. And then let's take a limit of that. Say we have phi j. Say let's take a subsequential convergence, for instance. What can be the limit? Normally, normally normal family argument will give you the limit. The limit might be by chance it'll become the automorphism group of target domain. Except that when the limit completely degenerates, if it degenerates to a point. Why does it happen? That happens exactly because an interior point of omega j, for instance, that goes to an interior point omega j by a biolomorphic self-map, automorphism of omega j. But as j goes to infinity, that sequence, even though the source point can stay inside, say origin, the image point can gradually move to the boundary of omega. It's possible. If that happens, then the limit is just a constant map. Constant map is not obviously automorphism. So in that case, you have no convergence of groups. So what you need is that there has to be some point in omega j. Let me use the word for a moment. Let's say I have omega j is moving, and then while it converges to some particular domain, so here's my omega 0, say, here's my omega j, and omega j will converge to omega eventually as j goes to infinity. I take one point over here, which is way inside, but then we think about the action by phi j's. Okay, the automorphism group. By the way, automorphism group of omega j is also compact. Automorphism group of omega 0 is compact. So for each fixed j, the orbit of this particular point is compact, and it's going to stay inside the domain. But as j goes to infinity, then the orbit might move, and then you can go to the boundary. And so what I want to say is that phi j, which is the automorphism of omega j for each j. Phi j action moves p, but only in the interior. If it does not go off to infinity, then we can use normal family argument, right? So how can you separate some interior point which is stable under all this automorphism action as you perturb the boundary? And that's first key issue. Right? So that's what we call stably interior points. And stably interior points can be obtained if we think about some invariants. We chose to use Bergman curvature, holomorphic sectional curvature of Bergman metric. In the strongly pseudo-convex bounded domain situation, it is known in 1978 by Paul Klembeck. Klembeck was a student of Robert Green's, actually. Paul Klembeck proved, it's not Kentucky, this is Kim and Yu. There's a Green, Kim Krantz. Anyhow, but we have this theorem. Klembeck's theorem is that if you have a bounded strongly pseudo-convex domain with C infinity boundary, and then as you go out to the boundary, the holomorphic sectional curvature converges to negative constant. He gives a definite value. That's holomorphic sectional curvature of the ball, which is -4 over dimension +1, complex dimension +1. So that was Klembeck's theorem. And then, to be absolutely honest, Green-Krantz paper uses Klembeck's theorem, assuming that Klembeck's result is stable. So in 2011, that's this year, a book is coming out in about a month or so. That's this one. Robert Green and Stephen Krantz and myself. This book has everything cleaned up. We have a stable Klembeck contained in there. And the Klembeck's theorem uses asymptotic expansion of Bergman kernel by Charles Pfefferman, the famous result. And that requires lots of derivatives in the boundary. How many, we don't know, but lots of derivatives. And so if it is 129, and then it's ridiculous to say C129. So C infinity is written. Anyhow, that was known. That's one reason why there is C infinity in the Green-Krantz assumption. The reason why I used red fonts over here, red character, is that this is something to improve. So we want C2. Indeed, it is possible. For a single domain, Jie Yu and myself proved Klembeck's result precisely with the C2 boundary. So, of course, we couldn't use Charles Pfefferman's asymptotic expansion because we don't know how to do it for the C2 boundary. It really requires lots of derivatives. So we used the scaling method to prove this thing. And then it turned out that while we were writing this book, all three of us were slightly concerned, actually a lot concerned, that the Klembeck's thing was just cited without perturbation issue. So we wanted to prove it, and we proved a little bit too much. Actually, it is correct that the C2 case with stability, we could do it with a new method, by this method. So here's some improvement over here. So by doing that, we have stable interior point. Okay. And what's Lu Qikang doing here? So let me explain that too. So the issue is not the Bergman curvature, but the issue is to prove this thing, right? So certain point don't go to infinity, don't go to the boundary. How do you do that? What one can do is that if the interior points go out to the boundary, if one point goes out to the boundary, this is another fact of life, that every point will be carried to the boundary. At the boundary, curvature is minus constant. Okay. As a result, the carriage was biholomorphism. Biholomorphisms are isometries of Bergman metric. Therefore, the holomorphic sectional curvature over here is also negative constant. If Bergman metric has negative constant, Bergman metric has many interesting features. I say interesting because it's usually understood as a bad feature. That if you have a covering space, one domain covers the other, for instance, because Bergman metric is usually defined on the bounded domain, classical sense. So let me just take a classical situation. One domain covers in a covering space sense by a holomorphic covering map. Then the Bergman metrics do not show any good covering properties whatsoever. Covering map is not an isometry, not local isometry or anything. And so it does not work very well with the covering map. That's a bad feature. But then it turns out that in this particular theorem, it's amazing that that bad feature is actually very good. That if a domain, although we don't need that full power, let me just advertise Lu Qikang's theorem. In the domain, bounded domain, if the Bergman metric is complete and has a constant holomorphic sectional curvature, then the domain is actually simply connected and it's the ball up to biholomorphism. That's quite a curious theorem, actually. Amazing theorem. And let me add an advertisement again, and this book contains rearranged theorem of the proof of Lu Qikang's theorem also using Bergman representative coordinates. And so all this interesting thing tells you that if a point is carried out the boundary all the time, then the holomorphic sectional curvature will become constant, and therefore Lu's theorem says that your domain is the ball. But we precluded that right from the beginning. So we do not have that. So certain points cannot be carried out to the boundary whatsoever. So that's what we call stably interior points. And that is sort of enough, almost enough to conclude the semi-continuity without conjugation issue. Let's say there exists some Lie isomorphism sending omega j, the holomorphic automorphism group of omega j into the target group as one-to-one homomorphism, Lie homomorphism. But anyhow, let's continue. And then if you want to do the conjugation issue, then we use extension theorem. This is another traditional thing now a traditional thing, which was a current topic for a long time, some time ago. Now I'm saying this, so I'm not young anymore, I suppose. Dan just had a birthday, but it's not my birthday. Anyhow, so the extension theorem should be done a little bit better than just the extension of automorphism of one domain. Namely, you want to do a simultaneous extension. What does that mean? Let me spend a few minutes to explain simultaneous extension. Extension theorem depends upon good coordinates, actually. So let me just draw a diagram. So here's a domain. Here's a domain omega. And it's going to perturb. But here's I'll just discuss the automorphism. Holomorphic automorphism. If I think about holomorphic automorphism, it's a map of interior to interior. It doesn't say anything about the boundary. It's a very good map in the interior. On the boundary, we don't know. But then what we would like to do is that if I choose a point P over here, then the image phi P is very close to the boundary because it's an automorphism. Yeah, we can do that. But then what I want to do, what extension people try to do, was that they try to find the very good, let me just draw shade a little bit past the boundary, includes the boundary. It does not have to go beyond the boundary, but up to the boundary. We want to find a good coordinate. So let me call it beta here. Beta of P, say beta of Q. These are maps into Cn, into Cn. I'm using a quotation mark because it's actually onto some open subset of Cn. Yeah. So this map is some coordinate. I'm going to use a Bergman representative coordinate, but coordinate system. Here's another coordinate system. And let's take coordinate system in such a way that the coordinate system sends P to the origin, here Q to the origin, and then this composition, all this thing commutes locally. It's a local coordinate. But this composition, so from here, beta inverse to phi and then beta, this thing becomes complex linear. That's the magic here. Complex linear. Once you have a linear map, even though it is locally defined, we know how to extend linear map. It's so easy, right? Linear map is just extended. And so this thing extends beyond the boundary. And so the non-extendability, if it is not extendable, or extendability, if it is extendable, depends on the shoulder of this particular coordinates, right? So if you have a nice coordinate showing that this map, linearity is a little bit too much, but suppose this map just extends, then the extension problem changes to the extension problem of this coordinate map, right? And so with this kind of conversion, you'd like to mention the stable extension in terms of stability in case when this coordinate is stable under the perturbation of omega. Now you change the perturbation and you'd like to mention something about the stability of these coordinates. And if I may spend one more minute, let me just say Bergman representative coordinates. By the way, the coordinate I'm going to write down is not the only known usable coordinate. The famous extension theorem in several complex variables belongs to, of course, Pfefferman himself, but later by Bell-Ligotzka, and then by other people too. And they used some variation of Bergman coordinates. Bergman coordinates was no good, actually, for their purpose. It's still good in many senses, but it's not that exciting. And so the Bergman coordinate is given by the following thing. So let's say WK at P of log Bergman kernel of ZW, kernel of WW. Very funny. This is the Bergman representative map at P. Very strange, eh? Yeah. Indeed, very strange. This map, which was named by Bergman as a representative domain. This is a map, not a domain, but he called it domain. Anyhow, let's say Bergman coordinates, because it's a coordinate in nice case. This is okay, because Bergman kernel is never 0 on the diagonal, so it's okay. But KZW, this Z and W are not the same. And so this kernel might be 0. Then that's okay as long as you don't have this interesting function over here. But we do need log function over here. Log of something 0 is terrible. And so there was a infamous conjecture that Bergman kernel never vanishes anywhere, which was very wrong. It was proven to be wrong for almost all domains in some sense. And in some other sense, there are still many domains with that conjecture is actually true. For our domain, actually, Bergman kernel doesn't vanish near the boundary because it's very close to the ball. That was proved in the other paper by Green and Kranz. But anyhow, the key point is that to show there's a stability on the perturbation of the boundary of these Bergman coordinates, then you have simultaneous extension. Altogether, we have semicontinuity almost done. So let me just continue to explain how to do this. Then you think about the domain defining function. You think about defining function. And then you think about the level sets. Not on the boundary, but slightly inside, sub-level sets. Those are not invariant under the group action, unfortunately. So what you do is you use Haar measure on the compact Lie group, and then you try to average the defining function so that the sub-level sets are invariant. And then sub-level sets are also smooth because of implicit function theorem. Near the boundary, defining function has non-vanishing gradient. And so you use implicit function theorem. And then you cut with the sub-level set, and you can make a metric double to create a compact manifold. Now you don't talk about domains anymore, but you talk about the compact manifold, metric double. This was all done by Green and Kranz. And using that, you have a weak sense, slightly weaker than Evans theorem, but we do have Evans theorem applied, and then we have a subgroup situation up to Lie isomorphism. And so that's okay. If you want to get the stronger version with the conjugate between closure of the domain, you not only use the sub-level sets and a little bit more intricate argument of re-averaging the sub-level sets using jth compact group, etc., and then you can obtain all those. So that's how you prove the theorem of Green and Kranz of 1982. That was semi-continuity. And then no one did anything to that theorem for a long time. Bits and pieces we did that. And then we wanted to do C2 version. And then we wanted okay, C2 version, and you can actually see from what I presented by far that C2 version without conjugation between closure of domains, without that, is already done because of Klembeck was obtained by C2, And then we don't need the extension theorem, I said. So for the conjugation, we need the extension theorem, but for just the semi-continuity in weak sense, it has nothing to do with the extension theorem. So we can just do this. But then once you get a horse to ride, this is an old Korean saying, then you need a squire. So we wanted a squire. So we wanted to prove extension theorem too. And there's a very clever person named Limpert who had the low differentiability and the extension theorem for the strongly slow convex case. Yeah? And so what you need is the stable extension theorem, stable Limpert. So if you just replace behaving like a calculus student, instead of Bergman coordinates, let's use Limpert's Limpert's coordinates. Then we have similar, except that this is not linear, but this extends forever. Not forever, but to the boundary. This thing extends automatically. So linearity is too luxurious. So we give up that luxury, but we want the extension theorem. And so can we do stability of Limpert extension? It turns out that by far we were doing very well with the C2, but here's a typo. It's 2 plus 2. We need 4 derivatives, I think, to be safe. But we are still working on the reason why we do not have preprint is that we try to make 4 into 2. So that's still going on. We don't know exactly how this will be done, but we have lots of reasons to believe that it's possible. But let me just state CK alpha with K at least 4. In that case, we have this full theorem of Green and Krantz all proved. And that's possible. So all these things require lots of analysis, lots of perturbation issues. But basically, this is the thing. And here's my old habit came out. This is now conjugate. These are closures. Okay? Sometimes people want to know something about the Bergman kernel, but I'm sure you know all these things. So I'm not going to explain all these things. And then I'll say a few things just to put the points at the end that I used the complete Bergman metric here and there. What about completeness? Do we know? And for the strongly slow convex domain, Bergman metric is always complete. That was first proved by Klaus Dietrich. Klaus Dietrich proved it in 1973. Later, Takeo Ozawa proved that for any bounded pseudo-convex domain, the Bergman C1 boundary, C1 pseudo-convex in that case. Anyhow, C2 case, there's no problem. There's some small controversy about the C1 case, but the C2 case, there's no problem. Yeah. So completeness follows by the strong pseudo-convexity, we assume. Yeah, this is all done. Oh, by the way, I'm going to mention one thing, which is a side issue, but this is necessary in the proof, to be precise. How far is Bergman isometry from being holomorphic? This was proved by in many contexts, but then I realized after a while. I mean, I was an assistant professor at Brown, and whenever I mentioned this issue, a quiet gentleman was always smiling, and later he said something about that. That was Professor Nomizu. And Professor Nomizu said that they proved this theorem in a much more general context, not just strongly slow convex domain, in 1958. I was born 1 year before then. So I told Professor Nomizu politely, saying that I was too young to understand that at the time. So, anyhow, this was an old theorem by Kobayashi Nomizu. What they proved is that on a domain with some sort of irreducibility, or to a more familiar term to geometers, if your Ricci curvature, Ricci tensor is some negative bound, pretty weak condition. If you have that, then any Bergman isometry in the identity component, any Kählerian isometry in the identity component of isometry group has to be holomorphic. So it's a very general theorem which was proved in 1958. So even though we come and go between Riemannian geometry and analytic geometry, complex analytic geometry in this context, we are pretty safe because we are not escaping anything from anything. So it's always the same. So that's all I can say. And okay. If I may say one more thing, is that after Fifth-Man's extension theorem was proved, again, this I don't know. I don't know in person, but I was told that in 1973, Bergman commented on Fifth-Man's extension, saying that that's way too difficult. And the easy proof is this thing. So this was actually credit goes to late Bergman. Stefan Bergman. So Bergman mentioned this thing, and I'm presenting as if this is a new argument, but no, this is actually Bergman himself. So sorry about telling all the old things. Oh, yes. Talking about credits, just one more thing. The stability issue was studied by Tumanov also. Not exactly in our context, but very close. And so all these things are done in the community in some sense. Okay, so that's it. Thank you.